In this note, we're going to look at trends in the periodic table. So one of the things that we quickly realize when we deal with chemistry and chemicals and such, and specifically looking at the elements, we find that there are very distinct characteristics and properties of each of the elements that are the defining characteristics of that particular element. However, what we also notice is that there are significant similarities in these properties and characteristics between some of the elements and some of the groupings of the elements. And so Mendeleev was the guy who initially started our modern periodic table, and he had the idea of looking at atomic mass and putting them in order of atomic mass. And he ended up with a periodic table that looked very similar to what we had. Later on, other scientists looked at putting them in atomic mass, or in order of atomic number rather than atomic mass. And so there are a few little discrepancies between that and Mendeleev's first version. Anyway, so let's take a look at our modern periodic table. You've already been introduced to it in grade 9 and 10, and now we want to take a look at some of the things that are particular to some of the things that we're going to look at later on in the course. So, the reason we have these trends and these different properties and characteristics is simply for identification purposes. We look at these things, and chemists really like to get things organized, and so the periodic table is organized primarily on the similarities and characteristics and properties of the elements. Now, when we look at groups and periods in the periodic table, the groups are the columns, the periods are the rows. Very simple. Let's take a look at our periodic table here first of all. So groups or families are the vertical columns, like these guys. And the the periods are the horizontal rows, going across from left to right. All right, so we're going to take a look at three properties that are pretty significant to our purposes. And the first one is atomic radius. And so the atomic radius, if we're looking down a group, so I know the arrow looks like it's pointing across, but I'm going to go from hydrogen, lithium to sodium. So looking as each new row is added, what we're doing, if you remember from your Bohr-Rutherford diagrams, which is what we've got here, the Bohr-Rutherford diagram, with each row, we add on another energy level for the electrons to occupy. And so that necessarily pushes the electrons further out from the nucleus. And so with each shell, we are increasing the atomic radius. So it causes the radius to increase. As we go across, we've got a couple of things happening here. First of all, with each successive element going across a row, so let's say lithium, beryllium, boron, carbon, as we go across that row, we're adding, yes, one electron to the already existing energy level, but what we're also doing is we're adding another proton to the nucleus. And so what happens is that adding that proton increases the positive charge. And because all of the electrons are in the same energy level, they are necessarily experiencing the same pull towards the nucleus. And since that pull is increasing with each element as we go across, they get pulled in a little bit closer. And so as a result, the atomic radius actually decreases. The next property that we want to look at is one called ionization energy. And so remember that ions are different from regular atoms in that they've lost or gained electrons, right? So if we have an anion, we have a negatively charged atom. It has gained some electric charge. some electrons. If the atom has lost electrons, then it becomes a positively charged ion, and we call that a cation. Now, the reason that we form ions, that elements form these ions, is because what we notice is on the periodic table, let me just back up here a second, back to our periodic table. There. So in our periodic table, what we notice is that our noble gases here are very, very stable. The other elements are actually, for the most part, quite reactive. And so what happens is, in order to become less reactive, in order to mimic this stability, the rest of the atoms will either gain or lose electrons. Let me flip forward again. Okay. And so in gaining or losing electrons, they become charged particles, and we call those charged particles ions. Positive ions, cations, negative ions, anions. So for example, chlorine. Chlorine has 7 valence electrons. And to become more stable, it wants to mimic the nearest noble gas, which is argon. And so argon has 8 valence electrons. So to do that, the chlorine actually has to grab onto 1 extra electron. And in so doing, it becomes the chloride ion, which has a 1- charge. Now, the trend that we want to look at is the amount of energy that's required to remove 1 electron from the valence shell of a particular atom. So in order to do that, we call that the first ionization energy. And the trend that we look at is what does it do to the atom in terms of how does the first ionization energy compare as we go across or down a row or a column in the periodic table. So let's first of all define ionization energy. It's the energy that's required to remove an electron from an atom. So our first ionization energy is the energy required to remove the first electron. If we want to move a second one, then that would be the second ionization energy, and so on and so forth. The energy is measured in kilojoules per mole. We'll talk about moles later on when we get to the second unit, or third unit of the course. But for now, it's that is the unit. Okay. All right. So let's look at the trend here. So as you move down each group, the first ionization energy decreases. And so let's think about what's happening here. The lone electron, let's go in the first column here, that lone electron that's outermost in each of these atoms, as you go down the group, it's further away. And it is shielded from the attraction of the nucleus by all the electrons that are below it. And so, because it's being held less tightly, it's easier to remove that electron. And so the amount of energy that's required to remove that electron becomes less and less and less as you go down the group. As you go across, because the electrons actually get sucked in a little bit closer, i.e. the radius decreases, they feel a stronger attraction as you go from lithium to fluorine, for example. And so the first ionization energy then increases as you go across the row. The next trend that we want to look at is electron affinity. Now this one's kind of weird because electron affinity, where the first ionization energy is how much energy is required to remove an electron. Electron affinity is the amount of energy that's either given off or absorbed by an atom to when you try to put another electron in. Okay, so it's kind of the opposite of ionization energy. Now, if we look at the elements, what we do is we find that sometimes it takes an awful lot of energy to actually force an electron in, because some of the atoms really don't want another electron. The electron that they do have, they want to get rid of. So things like in the first column, the alkali metals, those atoms really don't want another electron. They want to get rid of the one they do have. And so you need to force an electron in there, and that requires a fair bit of energy to do. So a high electron affinity means that a lot of energy is released when an electron attaches to an atom, and it's measured in kilojoules per mole. So for example, if I have fluorine on the other hand, it will very happily take another electron to mimic neon. And so as a result then, when you add that extra electron, the overall energy of the atom actually decreases. And so it releases some energy in the process. So there's a sign that's involved in electron affinity. So high electron affinity is actually a fairly high negative value. And a low electron affinity is a higher number but a positive value. So high negative numbers mean high electron affinity, whereas positive numbers mean a low electron affinity. All right. So the trend is, as shown in this periodic table, the electron affinity increases towards the right and increases going up the periodic table, so decreases going down. All right. So, for example, francium, cesium, barium, these guys would have a very low electron affinity. Fluorine, oxygen, chlorine, these guys have a very high electron affinity. That's the kind of pattern that we're looking at. The most useful trend that, and we're going to use this fairly extensively over the next few weeks, electronegativity. Electronegativity is not like electron affinity, although there is a bit of a similarity. But electronegativity is a measure of an atom's ability to attract electrons in a chemical bond. And that's kind of key here. It has to be within a chemical bond. So if two atoms are going to bond together, they share a pair of electrons, okay? And one electron gets shared more with one of the atoms over the other one, then there's an electronegativity difference between the two. So the atom with the higher electronegativity pulls the electrons closer to itself. Now, this is pretty closely related to the atomic radius, because within a bonding situation, the atomic radius dictates how far apart these atoms can get from each other. All right, so the number of protons in the nucleus increases at the same time the number of filled inner energy levels remain the same. So the electrons are pulled more tightly to the nucleus, resulting in a smaller atomic radius, right? So the atom attracts a bonding pair of electrons more strongly because the bonding pair can move closer to that particular nucleus. All right, so let's do a little bit of practice here. So first of all, which of these two elements has the largest electronegativity, and why do you think that? Oh, you should pause the video here so that you have a chance to figure it out. I should play some Jeopardy music in the background. Do, 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 do. Okay, maybe not. All right, so let's take a look at these. So sodium and rubidium. So they're in the same column, first column in the periodic table. Rubidium is much bigger than sodium, further down in the periodic table. And so in a bonding situation, electrons can get closer to sodium, and so therefore it's going to be the more electronegative of the two. Make sense? All right, sulfur and fluorine. Okay, same idea. So fluorine, smaller. Okay, sulfur has an extra energy level, so it's much bigger. And so in a bonding situation, fluorine is going to be more electronegative than sulfur. If I were to order these six elements in order of increasing electronegativity, that is the most electronegative to the right, what would that order be? Do 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 do. All right. All right. So the biggest of these guys, which one? That would be most likely. Well, and it's a metal, so it's going to be the aluminum. Is actually the largest one. You would think maybe the iodine because it's further down in the periodic table, but it turns out that the iodine, because of its strong, because of the number of protons in there, it actually pulls these electrons in quite closely. And so aluminum is just a little bit less electronegative than the iodine. Potassium actually would be the least electronegative. It's in the first column, so way over on the left side of the periodic table. Okay, so that would be the first one. So potassium, then aluminum, then iodine, then hydrogen, then oxygen, and then fluorine. Okay, so the order: potassium, aluminum, iodine, hydrogen, oxygen, and fluorine. All right, and there's the homework for looking at the periodic trends.